In this video, we will go through the steps involved in downloading an PID controller based position controller for a DC motor. So in the 20sim model, what you see on the right hand side is the mathematical representation of the DC motor, where I have used a velocity actuator to represent a DC motor whose output is connected to a spring damper followed by a spring and a transmission box, a lossy transmission box coupled with a bearing. So the output of the bearing is fed to an encoder and given to a position controller, which is PID based. The output of the position controller is given to two gain blocks like voltage gain and the motor constant gain. So these two values can be adjusted according to the different types of motors. In the position controller, there is a motion profile which gives a position profile output which is fed to the PID controller. So the task of the PID controller would be to follow the position of the DC motor as according to the set point of the motion profile. So the motion profile I've used is in pulse type and using only the position output. So these are the configuration of the motion profile. So this is start time, stop times. So you can see the rise time over here, 2, the return time, end time. The amplitude indicates the number of revolutions taken by the DC motor. The output of the encoder block is fed to this input port and again divided by an attenuation factor of 40,080, which is the counts per revolution value of the encoder used. So this in turn will convert the output into number of revolutions. So let's simulate this. So here you can see that this is the response of the PID controller and this is how he's controlling the position output of the DC motor. So the blue one line is the position output from the motion profile and the pink one is the simulation output. I can rename this for the better representation. So you can say position dot simulation. Yep. Now if I change the PID parameter, I open the parameter, go to position sub controller PID sub model, go to PID block and set the KP as 1. So now you can see that I reset the simulation. Now you can see that the simulation output is very closely following the motion profile. So we will download the experiment with both factors of KP, that is 0.01 and 1. So I start by downloading this. I go to tools, real-time toolbox, C code generation, select the 20sim 4C toolchain and the submodel position controller PID. So as this is a previously stored project, you have to select the rotary inverted pendulum template. So the board is connected through the LAN network to the laptop. So click apply. So the outputs are already connected. The input of encoder 1 motor port is connected to XDIO1 and also the XDIO1 pendulum output is connected to XDIO1 channel. Click on apply, compile. So once the compile is complete, you can click on upload model. So I've set the discrete time interval is 0.002 or 500 Hertz. Click on apply. We have to also log the outputs. So click on this button. So you have to select at least two variables, which is the encoder to rev motor output, this one. So you have to click on this one and also the motion profile X so that you can compare the output with the actual set point. Click again here and apply. You have to make sure that you remove the horizontal shaft from the motor, otherwise you can damage the setup if the things are not working properly. Now let's run this model. So you can see the motor goes clockwise. comes back anti-clockwise to its original position. So this is what you see the output over here, which is not following the set point. The pink one here is the set point. Now let me change the PID gain constant. So I set the KP as 1 and rerun the model, upload and start the model. So here we are. So there you can see that the actual response is very closely following the set point. Let me store this value so that we can compare it. So you just save in the project as position underscore PID log. Okay. Close this and close the 4C project. Now in the simulation model, I set the parameter of PID. So open the position control PID, gain as 1 and start simulation. So this was our simulation response. Now let's add the recorded value. So to do that, go to library, look for signal, sources and data from file. Also download a signal monitor. Double click on the file data and browse for the log file. So you can find this in C drive, temp folder, 20sim4C project folder, position controller PID, log, and this was the file we created. Select only the encoded derived motor output because rest we are not using it. Connect the output of this file data to the signal monitor. Let's simulate this. Okay, I have to recheck the model. So in the window 1, you can even add the curve which is of your signal monitor, but this has already been added. You can see the position dot measured. So this is signal monitor plot output. So this is selected in red color. I can change the thickness. Yeah. So you can see that the red one is very closely following the simulation data and the set point. So this is how the experiment works in the real world and in the simulation model. Thank you very much.